Thank you for coming to this introduction and tutorial for the Atom Power Monowave 200. My name is Diana. I'm from the Thorsten Hegman lab. So first, we are going to learn what is microwave-assisted chemistry, what is microwave radiation, how does microwave radiation generate heat, why use microwave-assisted chemistry, getting started, converting conventional protocols to microwave protocols, what solvents to use, which online resources are there available, and then we'll go specifically to the instrument and talk about the monomode cavity, safety, consumables, and how to prepare the monowave, how to operate the monowave 200. So what is microwave-assisted chemistry? It is the science of applying microwave radiation to chemical reactions. This can be done with organic synthesis. You can synthesize natural occurring polymers such as peptides or synthetic polymers. But for this particular machine, you cannot do peptide synthesis because we have the wrong setup. You can also perform microwave-assisted inorganic nanostructures preparation, among other. So what is microwave radiation? It's a form of electromagnetic energy that falls at lower frequency at the end of the electromagnetic spectrum. So around 300 megahertz to 300 gigahertz. Like any other electromagnetic wave, microwave radiation travels at the speed of light and consists of two oscillating fields, an electric field and a magnetic field. Microwave photon energy is relatively low and affects only molecular excitation. So how does microwave radiation generate heat? So the field component of the microwave radiation is the primary responsible for heat generation, interacting with molecules via three types modes of action. You have the dipolar rotation, ionic conduction, and the interfacial polarization. In dipolar rotation, a molecule rotates back and forth constantly, attempting to align its dipole with the ever-changing, ever-oscillating electric field, and the friction between each rotating molecule results in heat generation. In ionic conduction, a free ion or ionic species moves translationally through the space, attempting to align with the ever-changing electric field. And similar to the dipolar rotation, the friction between those moving species results in heat generation. And the higher the temperature of the reaction mixture, the more efficient the transfer of energy becomes. So in both cases, the more polar or ionic is a species, the more efficient the rate of heat generation. In interfacial polarization, it's a mixture of both. So why use microwave-assisted chemistry? When you use conventional chemistry with a hot plate, the heat flow is from the outside to the inside. The efficiency of heating is not that high, and it's only efficient at external heating. And there's no specific temperature. So what dictates the temperature that your molecules or your reagents experience is depends on the solvent that you're using, on the boiling point of that solvent. So usually you add enough energy to boil the solvent, and that's the temperature that the molecules or reagents experience. So compounds in the mixture are heated equally. There's usually a decrease in the reaction rate, so reactions tend to take longer, and it needs more solvents. But meanwhile, when you use microwave chemistry, the heat flow is from the inside to the outside. So there's a very efficient internal heating. And with a specific temperature. So now you're not restricted to the boiling point of your solvent. You can go beyond that temperature. And a specific material is heated. And there's a usually increasing reaction rate. That means the reactions will be faster. And sometimes you need no solvent, or you need less than for conventional chemistry. Therefore, microwave chemistry is considered to be green chemistry because it's more energy efficient, needs less solvents. There's usually no workup that it's needed afterwards, so you save many resources. So getting started, you may have some initial questions. For example, which solvents or reagents are suitable for microwave irradiation? Usually the rule of thumb is to use polar solvents with thermal stability, so solvents that do not decompose at high temperatures. And what is the thermal stability or the composition? You have to, before you use a microwave, you have to do your homework and check if your reagents are stable at high temperatures. Otherwise, you cannot use it for microwave-assisted chemistry. And so you have to consider solvents or reagents changing their properties at higher temperature. Is flash heating required? Usually the starting point is around 10 minutes. You do a holding of 10 minutes at 120 degrees. And then when you are optimizing, you tend to increase the temperature rather than the reaction time. And how can we fit limits of chemistry with the equipment? You usually start by applying small volumes, unless you already have optimized the reaction. So, as I said, the rule of thumb, for every 10 degrees of temperature increase, you usually get a twofold rate acceleration. So, as an example, if you are performing a reaction at 80 degrees that takes 8 hours, if you use a microwave with sealed conditions under pressure at 160 degrees, in a temperature of 160 degrees, it will take approximately 2 minutes. So there's a decrease of reaction time with the increase of temperature. So what solvents can we use? So as I've explained before, our microwave works, so you need to have solvents that are dielectric or polar. So here I've did a color scheme, so green, dark green to light green, where we show the very good microwave solvents that absorb very good microwave radiation, and then in red, the ones that have very low pore absorption. But if you are performing a reaction where your reagents are only soluble in these, you can still perform. You can use passive heating elements, such as a silicon carbide, which is a semiconductor, and it absorbs very well microwave radiation, and it will heat up the reaction mixture above the boiling point of these pore. They can also be called transparent microwave solvents, and you can perform a reaction. So the company that sells the microwave, Anton Par, has some very nice online resources. Here is the link, where you can get some free database where they have more than 1,000 publications with microwave reactions microwave synthesis. So you don't have to think about what are the setups. You can already find everything or most of the things here. If you don't, there's a protocol converter where you can convert conventional chemistry to microwave. And you can also have some tips how to configure the machine so that you can perform your reactions. They also have a very nice book available for you to download for free. So let's talk about the Monowave 200. It's a single mode apparatus, and it creates a standing wave pattern. That means that the sample is located where the intensity of the microwave radiation is the highest, and therefore only one sample can be measured at a time. And it's only suitable for small-scale synthesis. Safety. Since the microwave is located in a chemistry lab, you have to wear PPE at all times, so safety glasses, gloves, lab coat. The machine is very sensitive to acids, so if your reaction needs acidic conditions, I'm sorry, you cannot use it. Because although we are reacting in a sealed vessel, there can be leaks, and these leaks can result into corrosion of the equipment, which can also cause irreversible damage. And the same with explosives. We should not use epoxides, etc. The machine needs to be under a constant pressure of compressed air. It should be between 5.5 to 6 bar, and you shouldn't mess with these setups. So do not play with the flow regulator. Leave everything as it is. There's always the risk that meanwhile, during your reaction, the reaction vial can break. In that case, you should contact immediately Harry or myself so that we can decontaminate the microwave and remove the glasses, the broken glasses of the vial. And during your preparation for the reaction, you should manipulate all the solvents and the chemicals in the fume hood located next to the microwave. So the consumables. We will have here available two types of reaction vials, a small volume one, the G10, and a bigger volume one, the G30. The G10 can take as a minimum volume 2 milliliters and a maximum of 6 milliliters, while the G30 has a capacity range from 6 to 20 milliliters. What you have to purchase is some Septra. There are silicon Septras. Here it shows they are reusable, so you can use it as long as they don't look like this. Then you have to throw them away. And then there's a cap to keep the septum attached to the reaction vial. It's called a snap cap. And they also are reusable. And here are the part numbers if you are interested to get them from Antonpar. So let's check how can we operate the machine. I don't know if you can see it. It's here. So the plug is here. The switching. So it's also doing a check, a system check when it starts to initiate. So this is a hand gloves on touch. It has a touch screen, and you have to wear gloves to touch it. Okay, so it finished. So how can we start an experiment? So first we tap task list. It's here. And then we want to create a new experiment. So there's an A, I don't know if you can see it. We press the A, and we can name the experiment. So I'll call it test. And then press OK. And then it goes to a menu that walks you out which settings that you can choose. So usually choose the standard, which is already highlighted in dark gray. So it's already highlighted, and you press OK. And now you have to select the type of vial that you're going to use. Like I said, we only have the G10 and the G30. I will use the G10 for this tutorial. So I select it. Now it's in dark gray, and I'm going to press OK. OK, yeah, I know. It's just telling me that I still have to fill up many things. For this tutorial, I'm going to choose a temperature. There's a temperature that you want to reach. I'm going to put 120 degrees. Press OK. And the holding time, I will hold it for 2 minutes. You can choose to heat it as fast as possible, heat to temperature in time, or cool down. But here I'm going to ask to hold the temperature for whole time, and then I can put here the time that I want it to be hold. And no, I don't want it to. Yeah, here, yes. I'm going to put 2 minutes. Okay. And then you can opt. It has a stirrer inside, and you can choose the speed. So here it's at the maximum speed, which is 600. I could put 250 instead. And then the cooling, it's when you can remove your sample. So I'm going to use water. So 55 degrees, it's the cooling temperature that is being added, and I'll keep it at 55. So I'm going to press OK. And now that I think I have all the settings for the experiment, I will press OK. So this is the G10, and this is the G30. I'm going to use the G10. Usually, you can use the stirrer bars. You put one inside so that your samples are homogeneous, and there's homogeneous heat. And then you have to get a Teflon acceptor, which has 2 different colors. There's this white part, and if you flip it, there's a bluish. So the white is with the Teflon. Can you see it? Yeah, this is the white with the Teflon, and this is the blue non-Teflon coated. And it is this part that has to be in contact with the lid, with the liquid, because it's more chemical resistant. So you have to put it facing the white, facing down. And then you place, this is the snap cap. I think you can see it. So where these indentations are, it's where it should face also down. You place your septra inside the snap cap. So like this. And you put it on top of your reaction vial, and you have to use both your fingers to close it. And you should hear a snap. So it snapped into place. So for this experiment, I have some water. And in order that you can use this vial, the G10, you have to have to use a polyamide ring that you have to insert inside the microwave cavity, reaction cavity, because it's only optimized for the thicker one, for the G30. So this is the cavity, and this is the ring, and I just have to put it there. Okay, and the reaction vial goes inside. And you can press start. So it will close, and it will start the reaction. So it's starting. So it's performing the first heating step. I don't know if you can see the lines. There's a faint blue line, which is the power of the microwave. There's an orange line, which is the temperature. So it's the first step is heating up to 120. It has reached it. Now it's doing the holding for 2 minutes.
So where is the temperature sensor?
The temperature sensor is an IR sensor which is inside the machine. So infrared sensor. There's another possibility if the machine is upgraded to the Monowave 400 that you can place a temperature sensor directly inside the vial, and you have more accurate temperature readings. According to the manual, the IR has an error of 5 degrees, while the temperature probe that you can insert inside has a 2-degree error. So it's more accurate when you use the probe. But at the moment, we don't have that possibility.
Okay, thank you.
No worries. And it's giving the elapsed time, how many minutes you should wait until the reaction is over. So now it's doing the cooling. You can listen to the fan, which is cooling the vial. And you see the temperature is already dropping. And this is the limit, the 55 degrees that we introduced. It should also give us a pressure reading, but I think I've recycled this Teflon septra 3 times already, and I think it might have a leak. So they are not very sturdy or very reusable, because you should have seen also an increase in internal pressure. There's a pressure monitor system detector. So it's almost finishing because it has reached the desired temperature. So the fan stopped. And it's only when, yeah, so the cover is being open. So that means I can remove the vial. And yeah, it's hot. So how can you save your data? So this is the experiment. We go to the menu, data, memory, and let's go to browse results. And these are some experiments that we've been doing, and here's the experiment that we want. So it's the test, so it's highlighted, and what we can do, we can export it. So we click export. You have to select it first, and you can print export. And you can, so there's a USB port here. So if you remove these caps, it exposes the USB port where you can put your USB stick. And you can export it as a PDF, as a CSV, Excel, PNG, or as RAW, or everything. And after selecting the file, and in this case it doesn't allow me because I don't have a drive, then you press OK and it will export. And you can only remove your USB stick when it tells you that it's OK. And that's it. So it's extremely simple, very easy friendly, extremely nice. So if you want to delete your data, so you go here. So you go to menu, data, browse, and now I will select this, and you can load the data, so you see your plot, and you can save the method. We already saw how to export it. And we can also delete. So I will select the test and delete it. Yes, and it's gone. So from my side, this is the end of the presentation. I hope that that you're curious and that you want to try it. I'll be here to help you with any questions or to assist you with setting up your experiments. And yeah, so happy holidays, stay safe.